My name is Brianna Curl, and I will be your moderator for today's webinar on Beat the Heat, Solving Thermal and Cooling Issues in Your Design. Before we get started, I'd like to address a few logistics and details on the GoToWebinar platform. If you are unable to hear the presenter or see the presentation at any time throughout the webinar, please let us know in the chat and we'll do our best to resolve any issues. If you have any questions throughout the webinar, please type them in the questions panel as they come up. We will have representatives ready to answer your questions directly during the webinar. With that being said, I want to thank you all for joining us for today's webinar and introduce you to our presenter, CT Gao. CT is currently a Product Management Director in the Custom IC and PCB group of Cadence Design Systems. He has been performing analysis, simulation, and product design in the fields of electronic packaging, semiconductor processing equipment, and micro-electromechanical systems for more than 20 years. CT received his BS from National Taiwan University and MS from the University of Texas at Austin, both in mechanical engineering, and his PhD from Stanford University in aeronautics and astronautics. Assuming we have time at the end, we will field some questions in a formal Q&A. And thank you for your attention. And now, over to you, CT.
Hi, thank you, Brenna. It's really exciting for me to be here today. And I'd like to start with a background of PowerPoint of Cadence. This is a very nice illustration of a PCB board with multiple components on top of it. And today we talk about thermal issues when we're dealing with the systems. So for thermal issues, there are three aspects, to my opinion, we should be focusing on. How the heat coming into the system first, then how the heat coming out of the system, and how the heat is transported in between. So those three elements and three aspects, I hope we could keep in mind, not just during this presentation, but along the way we solve the problems. But we will keep coming back with this heat coming in, heat coming out, and how heat is transported in between during this presentation. Okay. So let's go along. Briefly, we are in this semiconductor industry. We should review this Moore's law. It has been dominated in our semiconductor industry development for maybe half a century. Then basically it says between around 20 to 18 months, the critical size will shrink in half, or clock rate will go doubled. But recently we know the Moore's law has been hitting the physical limit. Like if we talking about 2 nanometer, it's just a few layers of copper atoms or a few layers of silicon dioxide. So when we hit this physical limit, then this device development is related to the heat coming in. So when the heat, we'll talk about later that when we shrink this size, then it comes up with a lot of a problem. Then the people coming up with this heterogeneous integration roadmap on the device. So this Moore's law development is worth of reviewing when we encounter these thermal problems. So next, let's look at how the thermal issues coming along with Moore's law's development. I still remember in about around this millennium, I was listening a presentation of the famous Andy Grove, and he predict a power cliff as Moore's law going along. It's because of the critical dimensions shrinking and also leak current coming into the device, then excessive heat generation within the device could end up with a power density on the chips up to like rocket nozzle or even our sun. Of course, we know the things doesn't happen like that way, because engineers or scientists just will try all means to fix the problem, to make things work. So it comes up with a high K gate dielectric, for example, or FinFET, or multi-core architectures, or SOI inventions, or even strained silicon, but it's not frequently used right now. But above all, the enhancement of chip performance is not only focusing on the clock rate increase or not increasing powers. we kind of leverage different block or heterogeneous integration along the way. But thermal issue will never go away, to my opinion. No matter is a shrinking the critical dimensions, or we want to put multiple IP blocks on one single interposer or silicon interposer or substrate, then this old problem of the thermal issues will come up with us along the way when we push the technology forwards. Traditionally, when we think about thermal and cooling issue, we'll think about it as a mechanical problem. I would say it will be more focused on the heat coming out of the system, that aspect. We put heat sink, we put the tin, we put all those materials trying to dissipate those heat out. And based on a research literature we have got, that 50% of IC failures are related to thermal issues. Then, of course, we know the electronic engineer will be responsible for all those circuit and the failures. But actually, if we could accurately capturing the electronic feedback of the device, that power is coming out of a current, then it will be not just possible at the mechanical level to capture that. Because in mechanical design, it will always lead to a simplified model or some over-designed margins that will miss some hotspot or current clustering inside the circuitry. And thermal actually is in a very strategic position here because it will link with the electrical design, because electrical will be closely related to thermal, and also will be related to mechanical design. So nowadays, if we want to overcome the thermal issues, it is actually a problem of a system level implementation among electrical, mechanical, and thermal. Next, let's look at how does a thermal-aware electronic design, what are those challenges inside? So as we all know that electrical performance will depends on the thermal profile. Electrical resistance will increase in copper, will increase with temperature. So the higher the temperature, the higher the resistance. Then the electronics or circuit performance, all those frequency, other electrical parameters will be affected due to the temperature profile. And on the other hand, we all know those joule heating is a current square times electrical resistance. Joule heating will introduce additional thermal sources or heat sources into the system. Then you can see the first two factors basically is a kind of could go into a worse spiral condition. That's what we call the thermal runaway. Then nowadays, the transient simulation will become critical in the electronic design, especially in our handheld devices like smartphones, because we have operation at a different modes, and the time varying power profile will be implemented in those handheld devices. Then we are not running or using our electronic gadgets in a static state mode. Then how do we handle this thermal profiling together with the power profiling in our electronic device will be critical. And of course, right now it's not just limited to a small device. When we go to the package and board, and transient simulation has become more and more important among all those designers, as we know. Here, let's look at the system thermal designs from a physical dimensions and how do we handle that point of view. From the top left, going to the bottom left, and to the top right, we look at the physical device, physical size from IC to package to system. And the last we will show some figures about the transient. From the IC level, electrical thermal co-simulation has been recognized as very important. Then, because inside the IC chips, you can have different multiple IP blocks to generate different heats. Then from that granularity and the small refinement we need to figure out how the electrical performance interact with the thermal performance. Then when size goes bigger, we go to the package and board. Designers are looking at the chip junction temperature inside the package and also any hotspot inside the assembly due to ET code simulations. To the top right is a traditional electronic cooling arena, and people are using computational fluid dynamics together with maybe finite element methods to resolve any flow patterns or heat dissipation out of these solid assemblies. Then bottom to the right, we show some temporal response of the devices. And because you see, we could implement some waveform into the devices. Then we watch video, we listen audio in our cell phones. So we want to know the temperature change or power variation as a function of time. So from small size to large size, then all those electrical thermal interaction needs to be co-simulated to give a more clear insight and guidance of a system design. From the methodology point of view, IC-centric, package PCB-centric, system-centric, usually people or designer, we have to use different approaches. Simply because in IC-centric approach, we talk about FinFET is a nanometer or small, or even smaller. Then for system-centric, we talk about data center towers. It could be a meter range. So the overall physical size spanned maybe 10 orders of magnitudes in size. Then in software simulation, from the software and simulation point of view, to my knowledge, there's no one single software can cover 10 orders of magnitudes physical size range. So in IC design tools, we all have this EDA or ECAD tool using ECAD approach, and the package PCB is kind of in between. Then people using finite element analysis together with the CFD. It could be a layer structure in 2D or true 3D structure, trying to resolve this thermal issues from a electrical, mechanical, and thermal interaction point of view. From system-centric approach, again, people are using FEA together with CFD. Then we're looking at both transient and steady state simulation, and electronic cooling from the steady state point of view has been very mature during the past several decades. I'd like to show you some examples we have been working on this system level thermal analysis. All those examples has been obtained by Cadence tool I'll talk about later in this presentation. First, this will be a leaf-run package. Then it is solved by a true 3D illustration and resolution. Then each bonding wire bonding pad has been resolved on this package. And the designer want to inject current into specific bonding wires to see the transient response. And apparently the current are changing with time. So we could resolve that heat dissipation and the temperature variation along with the time marching fashion. So this is a transient simulation at the bottom right, you can see, but also we can do steady state. When we can do this transient, you can do steady approach. And together with a PCB board, you can see the hotspot at each bonding pad and a bonding wire in real time of operation. The second example is a smartphone. You can see this PCB is inside the smartphone in a very packed environment. Of course, for a cell phone, we cannot put a fan inside of it. So here, the convection is basically doing buoyancy. It's a natural convections. But this PCB designer has to evaluate the hotspot at different operation mode. So at the bottom right there, and in the middle of the bottom, you can see there are two modes, and the hotspot occurs at different locations. So we have measurement correlated with simulation very well, and that true resolution of the PCB is also shown there. This will be a mock-up of that smartphone. Again, we just want to emphasize that the importance of the transient analysis, because from steady state analysis, you can see the temperature just goes up to a saturation values, just like a RC curve, right? But due to the operation, different mode of operation inside the cell phones, so designers may want to pump in large power to boost up performance at high frequency probably, and then doing this throttling. So when they reach certain temperature, then they tune up to the low frequency and then can go up to the high frequency again. So by dump in a lot of power in the beginning, they can boost up the performance to the design, but you can tell how many seconds or how long of this high-low frequency range will be very critical for the design. So the designer can evaluate a duty cycle or a time control of this power profile in this device. So here we just want to stress that not only steady state simulation is critical now, transient analysis will become the key element in all those handheld design. This one is I just want to show that we want to resolve the true 3D MCAD. In this case, we have a true PCB design with the package. You have different lead frame, die attach, mold compound. All those things can be resolved in true 3D. Then after we get this 3D models, we could do all those static or transient electrical thermal co-simulations. Then this figure this slide just show you that package temperature or PCB temperature or the lead frame. You can see on those two chips, apparently the power consumption are different, and also the location is different. Then here at the bottom right, you can see all those details inside the PCB, including every trace and every via. Transient is the same. The current coming into this patch, going into the package, and through the PCB coming out of this patch. Then the duty cycle analysis, timing will be critical to find out how the performance will match the design and requirements. Next example here is also a complex assembly. We talk about true 3D importation into the software. We could resolve a PCB board and the enclosure, the top and the bottom. Then we resolve the temperature distribution inside with this two package and all those components on top of this PCB and then at the bottom of the PCB. For computational fluid dynamics simulations, this is just a assumed conditions. You can resolve the flow is a cross section of the flow basically. Then with those fin design, flow rate, and the speed, we can analyze how we get the heat out of this system. This is a true 3D MCAD resolution of the assembly. This example is a laptop. Here we use the neutral file format. It's called ECXML. We can get all those model coming in. Then we can solve the global thermal CFD solutions, including temperature and flow patterns. And after we get these global solutions, inside this laptop, there's a very, very important motherboard. In previous thermal CFD simulation, this board will be simplified as a simple plate with maybe average material properties. But because Cadence, like we own this package and board design, so after we get these global solutions, we can dive into details using the global solution as a boundary conditions. And so we can resolve each via or traces inside this PCB, which is not feasible if we include all those details of the PCB and into this laptop to do overall thermal and CFD solutions, because they cannot just take care of all those details inside this PCB. The last example would be this another complex assembly, including fan, heat pipe, heat sink, and board and package and chips. And this one, the heat source, how the heat coming into the system is coming from the chips, and we could analyze the power map inside the chips through a IC design tool. After we get that actual realistic power consumption inside the chip, which is the main heat source, then we can do an analysis together with package and PCB and all those heat pipe heat sink to perform the thermal CFD global solutions. Then again, we can dive into details as we want. So this would be another example of how we can do system level thermal analysis. All those examples actually are performed by an integrated electrical thermal analysis tool we launched last year. We call it Celsius Thermal Solver. Just a wrap up of this feature, these features in Celsius Thermal Solver. Again, we have a steady state and transient ET code simulation, including mode-dependent power map, joule heating, including chip package and PCB assembly. We leveraged the massively parallelized matrix solver to produce a almost linear scalability in terms of performance and without losing any accuracy. On this tool, we combine a finite element analysis on the same platform, integrated for the user to go back and forth between solid and fluids or in combined. Also, we integrated with the current Cadence design tools like Voltus, Allegro, Innovus, and Virtuoso to provide a total solution from single IC to package to PCB, including now is commonly a focus of a 3D IC and a heterogeneous packaging strategy. A few words about integrations. Currently, we have an ongoing project to integrate Celsius Thermal Solver with the Virtuoso platform, SIP layout technology, and also Allegro technologies. We have a close integration with Voltus at this moment to get a chip power into the equation. Then so together with Celsius Thermal Solver's chip package board and enclosures capability to solve that system level thermal problems. One page summary of a thermal analysis based on package and PCB board. So from the Allegro here, we have an example from Allegro. You can have a pre-designed floor plan, or you can have a detailed design of the PCB board. We can read it into Celsius Thermal Solver, so we can perform 3D solid temperature profiling, including computational fluid dynamics. If the details of the PCB is so large in size, we could take advantage of the layer structure approach. Then we can resolve hotspots. On the right-hand side here is one of the example of a rigid flex PCB we directly import into Celsius from Allegro. I'll talk more about this example later. A brief summary of at this stage, I'd like to wrap up this Celsius Thermal Solver. We can do transient steady state thermal analysis from chip package and board, including finite element and CFD. Our accuracy has been correlated to lab measurements very well. Then we have this world-class parallelization technology to speed up the solutions time up to 10x without losing any accuracy. And this tool has been implementing to integrate with Cadence other design tools, including Voltus, Virtuoso, Allegro, and is readily available on a cloud platform. And next, I'd like to show how to operate the Celsius Thermal Solver and some demonstration. For the demo session of Cadence Celsius Thermal Solver, we are going to look at 5 examples. Before I demonstrate those examples, let's look at those functional modules of Celsius. Double-click Celsius, you'll see a window with functional modules. First one is solid object simulation for 3D structures. Second is solid object simulation for layer structures. The third one is fluid flow simulation. So let's click the first one. You see this window pops up. Basically, it could include a 3D structures, and all the things is in the 3D. We do finite element analysis here. Then if we click the second one, it will pop up a GUI very similar to our tool PowerDC. And it's a two-dimensional layer structure with a workflow panel on the left. The third one is a CFD, fluid flow simulation. This one is very similar to the first one, but since we have two engines, one for finite element, one for CFD, so we have this third module to take care of the fluid flow simulation. Let's go back to the first one, and I'll show you the first example from there. Let's make it a little bit bigger. So let's give a new project. Then we can import the file. From here, you can see we can import multiple. Let's go back to the first example. So you can here, I'm going to import a set file, which is a typical 3D solid model file out there. It's universal. It could be generated from any 3D solid model software. But in addition to set file, we could import it many data format. And for 3D, we have IGES, we have step file, and set file. For design file, we can import it cadence speed file, MCM file, SIP file, etc. So let's look at this imported set file. Open. See, this will be a simple model of a PCB board with some connectors or components, inductors showing here. It's created from our cadence tool Allegro. So you can have a 3D illustration of all those components. On the left, the panel, you can see there are multiple components output from Allegro. For each one, right now the material has not been specified, but they could modify the illustration colors, etc. That would be very straightforward. Then, in order to assign materials, user has to tell the software what material will be. We have a material library built up. So say I pick copper and FR4, just for example. I exported it to the current design. Then I click OK. Then I click this component. I could choose material from the list I have built. So the user has to be specified material properties. Then we are going to implement a automated process from the output of Allegro. Say this is a set file. Set file doesn't include any material properties, so we may be able to create another file like a text file. Then we can import it at the same time or together with the set file. Then all the material property are already assigned there. Another one for thermal analysis, another key point is to assign a heat in, like I already mentioned, how the heat coming into the systems. So we could say this will be generate 2 watts, then we can click this objects, then we have a heat sources and 2D, 3D heat sources, then we can specify 2 watts there. It should be very straightforward. Then after the material properties and heat in to the system as assigned, then we can do the simulation from there. We could do CFD simulation. We can also do a say this, if the bottom of this place is attached to a big heat sink, then heat sink is maintained at say 20-40 degrees C, then we can specify the temperature there. Or we can do CFD simulation. So next, I'd like to show you, we do CFD simulation on this example. Let's close this window, then open the third CFD, then imported another file I already created for the same project with the extension 3DTH. Notice that the 3DTH file for the CFD has a box surrounding all those objects. That box is needed for CFD because users has to define a flow region to perform CFD simulation. And for this example, I already set the power on the individual 3 components. You can see one here, another here. The 3 component has power. Then we can specify a flow condition. In this simple example, I specify the flow coming from the back on this surface. You can see there's a flow volume, velocity there. Then all other surface also has a conditions. So the back's coming, a flow coming in. Then the front got to be open. Then the top, bottom will be symmetric. So after we set up all those power and heat coming out of the system, all those conditions, then we can run the simulation. I won't run the simulation here. It has been pre-run, but I like to show you the examples of the results. This will be the post processor. Then you see thermal results. Okay, now the results read in. Then you can see this is the temperature distribution of this whole flow box. So we could have some multiple operation. We turn off the flow region. Then you can see the solid inside. That's the temperature distribution. And I click the range. You see more clear from 30, 31, 32 degrees C to very high 75 degrees C. Okay, that's the solid parts. Then how about the flow parts? Flow, we have multiple choice to show the flow. Can show streamline, cross sections at different locations. So here, let's just show you the cross section. This will be the cross section. Then they have a different section cutting at different sections. So if we cut this way, then there will be that in the Y we could see more clear of the flow. Then if I turn off that, you'll see roughly the flow coming from this side to that side. So it would be best we could see the solids. Yeah, that's what I want. Then you can see this all the temperature distribution. So you can see high temperature behind this tall component. Then how about the flow patterns? So we can click more better showing. Well, then you'll see this really hot air behind it. Next, I like to see the flow pattern more clearly. Then I could use another function in the post processor, which is showing the flow arrows. A little bit more operation here. Illustration. Let's plot velocity. You can see the velocity is from 0.6 to 0, of course. Then you can see the flow pattern surrounding the object. Okay, and temperature-wise, you can see the temperature is low temperature from there is 22, and there's a hot about 50. Then there's a flow pattern surrounding this whole assembly. And by the way, the about the section view, we could easily move and show at different section by moving this panel. You can see all the flow patterns and temperature distribution of this example. The second example, I'd like to demonstrate that rigid flex PCB containing 4 small PCBs. Let's open the solid object simulation with 3D structure again, and reading that the file we already created. This file, 3DTH, already been imported. It's also created by Allegro in step file in true 3D solid modelings. So by the way, Allegro can export step file and the 3D model easily, but we have no problem to read in all those step file and the step file. Okay, remember this, the first example we just show is created by SAT file, set file. This will be created by step file. Then after you read it in, you can see all those details. even one of the PCB here has multiple layers. You can see it's pretty complicated. Then after we read in all the materials, basically we could group them into different category. Say right now I can group it by material. So so for simplicity, we just put the copper, FR4, polyimide, and the solder mask materials there. So if I hide some material, say I hide polyimide material, although that will be those components, then if there's FR4, we just put it there as FR4 materials. Then if I hide those materials, then I hide solder mask materials, then it will be all the coppers. You can see the copper and the polyimide, like the molding compound materials, which is arbitrarily set up here. But notice that for each layer, actually, the via and trace are already resolved there in true details. So this model is not a small model, but you can see the bending rigid flex also showing there. I like to show the audience here that the capability of a Celsius thermal solver can read it in all those complex 3D geometries. So in terms of heat sources, we also put some heat sources on this model, trying to see the thermal response due to this heat coming into these systems. And here we didn't run the CFD, but we could. For another analysis type of capability, we could specify heat transfer coefficient at the surfaces. It could be a constant temperature or constant heat transfer rate out of the systems. Then I'd like to show the results we already run, just like before. Okay, that's the model itself. Then we can turn on the temperature. So that will be the temperature results. You see every details and the components distribution, just like we have seen before. So this example show you we could import a complex geometry in 3D and perform thermal analysis of this complex assembly. So when the designer want to change the power on certain components or move around the components on those four PCB board, they can do so to quickly obtain another run of a thermal analysis results to optimize his or her designs. Next, I'd like to demonstrate that the smartphone mock-up model I showed in the presentation. So let's go to the CFD module of Celsius thermal solver. Then we will load that model we have created. And that I believe that's a set file model. But we have already created this 3dth. .3dth is a specific extension of Celsius thermal solver. Then we can open it. You see, as before, we need to specify a flow region like outer box to specify where the flow has action. So of course, we can turn it off to hide it. Then that will be the model itself. Then let's look at that model for more details. So the parts, we have air inside. We have air inside around the component. We have top glasses, all those components. So I could hide it. Hide the glass, hide the top air inside. Then you'll see all those components inside there. We have a battery, we have a PCB, then has other components here. Then if I turn off that aluminum cases, hide it, then basically we see all the components. We have PCB, multiple PCB. We have a tin material underneath the battery. We created a mock-up according to the real configuration of a smartphone. Then regarding the power input, you see we can specify all those power inside the cell phone, including battery, all those module like RF packaging, named LTE. Then we could specify the condition. The flow condition here, we specify the flow coming from the bottom surface going to the top surface, and it's basically using an open environment because we cannot install fan inside a smartphone, obviously. So remember the first example, we show a forced convection. We have a flow coming into the flow domain, maybe from the fan or other apparatus. But here for smartphone, basically we cannot have a fan, but we need to rely on the natural convection of the air. So after we specify all the things, including material properties, then we can carry on this CFD simulation. So I'll omit that running and show you some results like before. Post-processing, we launch the post-processing. Then again, it has this result coming up. Then I'll show some, turn off the flow region. You see the cell phone. You see temperature profile. Then we could turn off some air, glass, like we see before. Then we could have a cross-section of the flow. Now, just like before, we have this example showing here for this case. Then, but for the section slice, right now is a temperature, so we want to see the flow. So we need to plot it as velocity. It's there. So the velocity, why is the red on the top? Because the velocity, if it's a natural convection, the air coming from the bottom and surrounding the smartphone go to the top. And apparently the velocity at here has the largest value. Here is about 0.1 meter per second. And like before, we could plot the velocity flow pattern, a little bit operation, turn on vector, then make it bigger. Then turn on and color it with velocity. Then we see the flow surrounding this smartphone, and the pattern is a natural convection because the hot air will go coming from the bottom to the top. And of course, we can also plot the streamline and all those fancy illustration, but I won't show the procedure here for the sake of time. In the fourth example, I like to show the capability of a Celsius thermal solver to handle the details of a package configurations and the electrical thermal co-simulation. Let's go back to the 3D structures. In this case, we are loaded a assembly of a leaf frame package on top of a JEDEC standard board. And the JEDEC standard board will be the 4-layer standard JEDEC board with a different metal percentage. And the package will be a 100 leads leaf frame package. So let's load it, that model. This model again is a true shapes, so it will take some time, but no more than about 30 seconds on my laptop. So even you see, you see a PCB board. They have a 4-layer of a PCB, JEDEC standard. We imported, we can create it according to JEDEC standard. As for the package, you can see that will be a 100 leads leaf frame package. Then we create all those leads inside Celsius. Then, like before, I could group the model into different materials, like here. Then I can hide it, all those dielectric material and bore material. Then, because I want to see the package in more details and more compound, also dielectric, I hide it. So all the structures are created from a zip import layout. Then it will be according to the true design. You can see all those bonding wire, bonding pad, and and we can create the silicon chips inside Celsius. So that will be the package design with the lead frame. And for electrical thermal co-simulation, we could specify power on this silicon die, and also we can specify voltage, VRM, and we can specify current sink for arbitrary location of a wire, bonding wire. The user want to see if they pump in a certain amount of current, see how the joule heating due to the electricity will be added up to the power generation inside the silicon chips. All the components show up. This will be our assembly. Then after running the simulation, I'd like to show you the results. Okay, like before, I turn on the temperature. You see, that's the overall temperature profile distribution of this assembly. Then let's look at the detail inside the package. In this case, let's turn off everything, but only turn on silicon, gold wire, and copper. That will be the lead frame. So adjust the range of temperature. See, in this case, you can see apparently the designer pumping the high current going through this wire and coming out of this wire. Then we can see two wire because of the electrical or joule heating introduce additional heat sources. So actually the hotspot is on those wire. So the user can determine if those wire can sustain certain temperature, well, will break, or the together with the power inside the silicon chips to assess overall thermal response or thermal profile of this package if they put this package on the JET extender board for thermal characterization. The last example I'd like to show is a assembly of a package and board where both the package and the board are having a true detail configuration, and we can do electrical thermal co-simulation. Of course, we can do thermal only and the CFD for static and the transient analysis, as I shown in the presentation. So this example is a package and board assembly first. So it's a lead frame package. There are two dies in the package, and there's a customized PCB board for evaluating the performance of the package. And there's an inductor next to the package. You can see here we make some component transparent. You see some details inside. We have a bonding wire, bonding pad. We have two dies, and there's a inductor, and this is a customized PCB. So detailed setup, just like we have shown you before, including material properties, boundary conditions, power input. You have a different power. There, as I said, there are two power. There could be a power in the inductor. They have a power in the controller and the current. For electrical thermal co-simulation, the current can be input into the system through different patch, like we shown here. So it depends on the designer and the purpose of this whole assembly. So after we specify boundary condition, material properties, then we can perform the thermal analysis like before. Let me show you the results to give you a flavor of how this electrical thermal co-simulation can give us. Temperature, let's run temperature before. Yeah, this will be the results. Then like before, let's turn off this inductor. Turn off some board materials, mask. Turn off this molding compound. So we can see that's the true shapes, including bonding wire, including all those configurations and the via configuration inside the PCB, okay, hot region. So we can plot different locations. Then you see the hotspot. So we can easily play with the color scheme or the temperature range to see the details within this assembly. Of course, we could do CFD simulation like before. Here we show a natural convection results, the cold air coming from the bottom to the top, and all those component packaged in the PCB board are put into this orientation, like a vertical, the normal coming out of the screen. So you can see the cold air coming from the bottom and go to the top at this cross section. Also, we could do a forced convection CFD simulation, like placing this assembly in a wind tunnel. Here is the CFD results for forced convection. The setup is like put into a square cross-section wind tunnel. The airflow coming from the right-hand side surface to blowing to the left. Then you can see the flow will be blocked by the components and PCB board. So you can see all those flow pattern and rebouncing flow and vortex flow, and together with the temperature distribution and hotspot in the package. So all those natural convection and the forced convection CFD results could be set up like we talked about before in Celsius thermal solver. Okay, now this concludes all those example demonstration. Thank you for all of you attending this presentation webinar today, and I hope to contact with you if you have any question in the future.
Thank you. So at this moment, we will go into a Q&A. So if you have any questions, please ask them within the questions pane now. And let's see, our first question, CT, is, does the user need to create the CFD model for the thermal simulations, or does Celsius already come with some power maps and information for the ET co-simulation?
The power map on the chips coming from user supply. You can use IC design tools coming off the power map. And the solid parts, say you have a package, a board, as I said, we can read in the SPI file, MCM file, board files, SIP file. Then we can create that 2D layered structure or 3D like I just shown. Then we can use those solid model imported to create a CFD model. That CFD model could be as detailed as the solid model, or we can have a equivalent or simplified model. It depends on the model size. So the user doesn't need to recreate a CFD model. They can create it based on the solid model. Then we have all those operations ready inside our tool for user to easily create a CFD model to do CFD simulation. Then after they got a CFD solutions, they can extract the CFD solution at the solid boundary surfaces. Then if they want to do detailed thermal profiling inside the solid, they can do that as well. So there are many flexible options there, but they don't need to do twice, create a model.
Okay, thank you.
Yeah.
So our next question is, can the software produce animations of heat flow?
Animation functions already in the post-processing. We use this post-processing. They can do, if it's a time animation, it's already there. So I presume the heat flow, meaning the temperature variation, then of course we could do that. Say temperature 100 here, and at the end is 0, then the other end it becomes from 0 to 100. That's post-processing. We could do that. The heat flow will be shown as a temperature profile.
Okay, thank you. Let's see what else we have here. My company uses Power DC for ET co-simulation. What does Celsius add onto that flow?
Power DC. Power DC is limited to steady state. There's no transient analysis. And Power DC does not include CFD, computational fluid dynamics boundary conditions. The Power DC, we all know heat needs to be dissipated out of the system. In Power DC, how the heat is dissipated out of the system through convection, no matter it's natural convection or forced convection, are coming from a empirical formula. It's not coming from full CFD solution. So Celsius added in transient simulation and CFD integration compared to Power DC.
Let's see what else we have. For the chips with thermal pads, which model among packaged PCB or system is used?
Chip with thermal pad. So the thermal pad is under the chip. If it's a true 3D illustration, then we could resolve that. If it's a thermal resistance number, we could also include that. So basically, if we have it could be simplified or model as one single thermal resistance, or if it has 3D structures, we could directly simulate that. If the question is about thermal VS there, then it will be inside the chips. And again, that will be for Celsius thermal solver for this tool. We could resolve true 3D, we could resolve 2D. We could also implement the traditional conventional thermal parameters. For package board, we have CJ, JBJC, tool resistor model, Delphi model included. And for others, we could, engineering implemented some thermal resistor inside the assembly.
Well, thank you. Let's add just one more here. I have a question concerning the possibility of mechanical simulation inside the software. What kind of tool exists for this kind of analysis, and is it possible to export the result of thermal simulation to do FEA mechanical simulation in another software?
It depends on what kind of a mechanical software. This tool also including thermal stress could be considered another type of mechanical. So for thermal stress, we could do that inside Celsius thermal solver. The thermal stress including warpage, as we know, or definition of the bird with a component on top of it due to CTE mismatch, coefficient of thermal expansion in 3D. That function commonly we encountered in package and board, we included in Celsius thermal solver. So if the question is regarding to output temperature results, temperature profile to do thermal stress, then the user doesn't need to have another tool. We have it. Then if for others, we haven't had a text format results output implemented right now, because we need to have more further study with our customer to see what's the needs and how we can better serve them.
Yeah, thanks. So looks like we still have some questions coming in, but unfortunately we are out of time today. However, if anyone has questions that were not addressed during the webinar, we will be following up with you on an individual basis. So before we sign off, I'd like to inform you of our next webinar on designing for assembly. So keeping an eye out for that information on that webinar as well. And thank you all for joining us today, and thank you, CT.
Yes, thank you, everybody.